Let me first mention what is the scope of this course, right? And I've just tried to put it down today in terms of what really will be covered, all right? First is that there will be, like probably all of today, will be more on an introduction, and that introduction will include both global and Indian energy requirements. Okay, and it's important because if the course is on renewable energy resources, okay, I mean, why firstly are we looking at it? So we need to understand the requirements, okay, and what are the compulsions, especially to look at renewable energy. Okay. Second is that uh, there is a nexus between energy, environment, and sustainable development. Okay? And we need to understand it. Like, for example, if you look at energy only from the viewpoint of availability of feedstock, raw material, that's only one part of the story. Okay? On the other hand, if you are exclusively focused on environment, then also it's a complex matter because renewable energy today may not be able to provide all of the energy that we require. So we really need to understand both from the availability of raw material point of view, what are our unique advantages in India and over in the world, what is the scenario, and well, everyone knows, everyone is hearing about climate change, environment, it seems to be playing havoc. There must be some relationship with this course, okay? So that's something that we will need to discuss. Third is what are the various forms of renewable energy resources? Okay, I think some of it would be very clear to all of you. Can I ask some of you what would be some of the renewable energy resources?
Sir, biomass.
Biomass. Okay.
Sir, solar energy.
Solar energy. Great.
So from plant sources?
Biomass.
Geothermal energy, sir.
Isn't it? Huh? Anything else?
Sir, wind energy.
Wind energy. So biomass, solar, wind. Okay.
Hydro, sir.
Hydro energy.
So from plant sources?
Biomass,
Hydro energy, sir.
wind, hydro.
So geothermal
Anything
energy.
else?
Plant sources?
Sir,
Plant
tidal energy.
sources. Plant, so that's what I'm saying, that when you say biomass, I mean, biomass of course is coming from plant sources, so it's already taken care of there. Or you can make it more general and say plant sources. What else? Anything else?
So tidal energy, geothermal energy.
Tidal energy, geothermal energy. Okay, great. Anything else?
Sir, gobar gas. Not exactly what, yeah.
See, actually, when you say biomass, of course, gobar is not really biomass, but you are saying animal waste. Let's put it that way, right?
Yes, sir.
Okay. Yeah, that's what gobar is. Anything else? Okay, doesn't matter. I think you've covered it quite exhaustively. But let me tell you that there will be a few which we don't really take into account every day. But those also, I think we should include. Okay, and I'll discuss those as I go along. I'm not going to tell you right now what I have in mind. Okay, let me ask you, what about nuclear energy? Is that a renewable energy?
Sir, it's renewable, but can we consider in green technology because that's
No,
hazardous
the
also.
course is renewable energy resources. Okay.
Okay,
Sir,
sir.
it's
Okay, sir.
not renewable.
So like it's a clean energy we can say, but I don't think renewable.
Agreed.
Okay.
Yes, sir.
So
It's a clean
nuclear is
energy.
a question mark, right?
Yes, sir.
But let me tell you, uh, we will be covering nuclear because, and I will discuss. Okay, I mean I don't want to get too much into it at this stage. Uh, well, what we would of course need to know is what are the actual nuclear, physical, electrical, chemical, and biological processes which are involved in all of this. Okay, because it's not just enough to know the utility, okay, but we need to understand the processes, quite well. Okay, and so that is something that we will devote quite a bit of time towards. Okay, also, how exactly are these things harnessed for anthropogenic activities? We need to also understand that how exactly. I mean, it's all there. The solar energy is there, but how do I harness it? How do I harness wind energy? Okay, so we will try and get into those details. Okay, and at the end of it, we will also have to ask that to what extent uh, are we likely to be able to replace fossil fuels with renewable energy resources? We need to have some kind of a understanding, okay, and hopefully, that will become clearer as we go along, and you'll be able to make your own judgment around that. Now, another thing that we will look at is what is the role of renewable energy in chemical manufacturing. Now, although I have said chemical manufacturing because you're at an Institute of Chemical Technology, but I think some of you have raised very interesting points, renewable energy in construction industry, okay, or in life science related areas, what do we see as the scope of renewable energy? Okay, that's something that we will look at, and I also would like, I don't know whether time will permit, but I would like you all to make brief presentations on one topic, maybe no more than 5 minutes, 3 slides, okay, on some idea that comes to your mind in the course of this course. And so that will have more towards the end, where each one of you will give some thoughts, around what you have learned, what you have understood, what we should do, maybe which government should pay heed to. Okay, so we will look at that. Now, another thing that I want you to keep in mind is, and I think one of you have talked about it, like waste energy. Any activity that you carry out with energy, there will always be some kind of wasted energy which is generated, and so I think although it may not really figure in with renewable energy resource, but first and foremost, we should try and minimize wastage of energy. Because it makes no sense to churn out more and more energy sources and on the other hand waste that energy. Okay, so this is something that we will need to look at. Okay, and you've also seen that I've put somewhere unconventional resources. I've said conventional resources, unconventional resources. Okay, like say for example, let's say each one of us. Do you think you could be an energy source? You could do work? Can you
Yes,
do?
sir. Yes, sir.
Yes, sir.
Right, and so if you look at animals, human beings, they can actually do. They can be the source of their own energy to quite a bit of quite an extent. And I mean, for example, the number of I see so many people going to the gym, and exercising it. You as well could actually do some useful work while doing all this. And so I think treat yourself also as a renewable energy resource. Okay. And I think, just take a very broad view of what is renewable energy. Okay. That's very important. Now, the other thing, like you mentioned, biomass, solar, wind, hydro, plant sources. Let me ask you, are these all very unique sources of energy, renewable energy, or is there anything in common among them? Is there anything in common?
Yes, sir.
What is in common?
So they have no waste and the energy is consumed and there is no any waste product or byproduct, sir.
Why? There could be.
Because the energy flows from the ecosystem in a cycle, sir.
Okay, okay. So you are saying it's a closed loop, right?
Yes, sir.
Okay. That's one interesting way to look at it. Anything else? Like, I've seen people sometimes are very particular about the choice. There's some people who will vouch for solar energy and say, I like solar energy. Somebody says wind energy. Somebody says tidal energy. Okay.
So
But
one more thing,
yeah,
there is no limit, sir, for the
there is no limit. Now, let me put this down. This is interesting.
So there is one thing that might be common is that the sun is the source of.
Wonderful. That is the answer I was looking for.
Oh, thank you, sir.
Okay. Uh, so let me just put it here. Although I think you all made some good points. Okay. One was that you said closed loop with no wastage of energy. This is debatable, okay, but I'm putting it down. Right? What was the other thing that you said?
Sun is
so
the
no
common
limitation.
source.
No limit in
limitations.
generation. Huh?
Yes, sir.
And then derived from the sun. Right?
Yes, sir.
These are right? Okay.
Yes, sir.
And
Yes.
that's what we covered. Okay. Now, I think this last point is something that I will spend a bit of time on. Okay. And now, let me ask you. You said, of course, this that derived from the sun, but how old do you think this knowledge is? That it's all derived from the sun? Is it that from the time that civilization existed, this knowledge existed, or
No,
did
sir.
it come
No,
subsequently,
sir,
or
from the
was it
existence of the earth, sir.
Yes, sir.
from the
From
existence
the
of the earth?
civilization.
Yes,
No,
sir.
no.
Yes, sir.
I'm saying, see, one is that you might be using your available knowledge and extrapolating to that time, you know. But do you think that, let's say, when life started on Earth, that people would have known that it's due to the sun?
No, sir.
No, sir.
Yeah, so it probably came sometime later. Okay, and there's another thing that many times religion, philosophy, actually there's so much of worship of the sun, etc. So people knew that the sun is very important. That I don't think there's any doubt about.
Yes, sir.
They,
As the
they
Lord
knew that.
Ram comes from the Suryavanshi family.
Yeah, I mean, so those things are known, but there were many, many unknowns. Okay, and so let me just spend a little bit of time, okay, talking about the sun. Okay, now, as we discussed, that even though many people have obviously intuitively talked about the sun as being essential for life on Earth, that's very well known. But actually, it was not even 200 years back. Maybe about 190 years back, or thereabouts, that this person, John Herschel, you know, in a very classic book known as the Treatise on Astronomy, uh, he had for the first time articulated in a relatively more scientific manner, what is the importance of the sun. You know, and so what he wrote is that the sun's rays are the ultimate source of almost every motion which takes place on the earth, surface of the earth. By its heat are produced all winds. By their vivifying action, that is life-giving action, vegetables are elaborated from inorganic matter and become in their turn the support of animals and of man, read man and woman, okay, and the source of those great deposits of dynamical efficiency which are laid up for human use in our coal strata, okay. So he linked up also the formation of coal, etc., with actually the sun, okay, and so this was probably the most comprehensive kind of statement which was made that what is the role of the sun. And although, as I told you, that people would have known for a long time, that the sun has a very crucial role to play, but they didn't quite articulate it in this manner, in this kind of a structured manner that these people did. Now, let me ask you, how old is the sun? How old is Earth? Or how old is life on Earth?
Sir, 3 billion years.
3
2 or 3 billion years.
billion. Huh?
Billion years.
Means 10 to the power 9, right?
Yes, sir.
Okay, wonderful. Okay. So the sun would have to be at least that old.
Sir,
Yes,
Or
sir.
not?
it is older than that, sir. Approx 4 billion years.
The sun would have to be older than that or younger than that?
Older, sir.
Older, right?
Older than that, yes, sir.
Yeah. Now this is where people actually got into difficulty. Okay. And so let me go through actually what happened. Okay, um, ever since this Herschel articulating that life on Earth effectively depends on the energy from the sun, and so people knew that if we know how old the life is on Earth, then we might be able to say how old the sun is, and from when it has been shining. Okay. Now, of course, people knew that the sun is producing massive amounts of energy. Okay, but the question was that where is this energy all coming from? Okay, and so ever since 1833, it was, and it was sparked really by this exemplary writings of John Herschel that people began wondering, where exactly is the sun getting its energy from? Okay, and the probably the first person who put a lot of thought into it was Helmholtz, and Helmholtz basically said that actually what happens is that the sun is actually collapsing, and there is a gravitational collapse. And because of this gravitational collapse, massive amounts of energy are being released, and that is the energy that is powering the sun. Okay, and when he was asked then that, how old do you think the sun would be, if this kind of a gravitational collapse and energy release were to happen? He actually was struggling to even come to a figure like 1,000,000 years, and there was this uncertainty suddenly that really how old is the sun? How long has it been shining? Okay. And then what happened was there was another person, who we have studied about, William Thomson, Lord Kelvin, who proposed one of the most important laws of thermodynamics. Okay, and Lord Kelvin actually also began, thinking that what Helmholtz had said is right. That there is some kind of a gravitational collapse, which is releasing energy. But then what happened was that they actually could do some studies by which they because if it gravitationally collapses, the expectation was that the temperature of the sun will continuously come down, and there was no proof that the temperature of the sun is actually reducing. Okay. The second was that they actually did a very interesting experiment where they allowed a crystal of ice, to melt on Earth. Okay, and we know how far the sun is from the Earth. And so it was concluded that if I take the distance between the Earth and the sun, and now if I look at the total surface area, which will be created by this total sphere, which is there, and from that they could make a reasonable estimate of how much energy per second is actually being released by the sun. This is a very interesting experiment that was done. But the big shock came, when, and from a very unlikely source, and that was Charles Darwin. You would think this is the domain of physicists, okay? that how long the sun shines and things like that. And no chemist, biologist probably would have much of a role to play in that, but the debate was really sparked off by Darwin. So what happened was that Charles Darwin, as you know, he was the man who proposed the theory of evolution, and he was actually studying a valley in England known as the Weald, Weald, and he was actually studying the erosion that occurred in that valley, and he was able to link it up with actually the way in which different species, etc., evolved in the valley. And I don't want to go into the details of that, okay? But what happened was that when he measured the erosion rates and linked it up with the species diversity, he came to the conclusion that life on Earth must have evolved over at least 300 million years. And so that's what he said, that 300 million years is what it would take, to get the richness of diversity of the kind of species, etc., that you see in this valley, But then when he wrote that in his book, in his famous book, Lord Kelvin, saw that and said, "What rubbish is Darwin talking about?" Because I, the great physicist Lord Kelvin, have worked out that the sun could not have existed for more than 30 million years. And that too, the 30 million years, he came after a lot of fudging. Helmholtz had talked about the gravitational collapse, and but they did not observe any cooling of the sun. So what Kelvin said is that the sun is constantly bombarded by meteorites, and so they are the kind of supplier of energy to the sun. And so they are again in turn constantly gravitationally collapsing and releasing energy. And with all his calculations, the maximum age of the sun that he derived was 30 million years. And Lord Kelvin was such a famous man that Darwin simply could not challenge him. Darwin got scared, and subsequently, his book in the subsequent editions, Darwin quietly removed the age of the Earth, and basically just because he did not want to get into a debate and a conflict with Lord Kelvin. But people all around began to think that maybe Darwin is right and maybe Lord Kelvin is not right. And there were also reasons why Lord Kelvin believed that way, because what he said is, and we have to go back to a period of around 1850, 1850, 1860, around that time. What they said is that at least gravitational collapse of large bodies can release a lot of energy. But on the other hand, if the sun is a source of fuel, and if it has to burn, because, they knew what are the maximum heats of reactions in chemical processes. And so they said that it's not possible, even with all this dimension of the sun and, knowing its radius and everything, and what fuels could possibly exist. They said that no, the sun will just completely burn out in no time. So there was a huge thinking, about how do you really reconcile these things? Okay? On the one hand, what philosophers and other great people have told us about the importance of the sun, and what they have calculated to be the age of the sun. Okay, and so this debate went on for some time, but it was actually leading nowhere. And the debate was revived really after Einstein proposed the theory of relativity. Okay, and when he proposed his famous equation E is equal to mc squared, and basically showed the equivalence of mass and energy, that people realized, that it's possible to release huge amounts of energy, from relatively small amounts of mass. Okay, so there was a revival because of Einstein. But let me tell you that today, of course, Einstein is very great and everything, but at the time that he worked out his theory, etc., it was really a theory of relativity. It was not a proof. Okay, there was no experimental proof that existed for what Einstein had proposed. And so, people knew, oh, great piece of work, but that's about it. Okay, but then what happened was that this person, Aston, okay, and you can see 1920, so almost 70 years after this debate had been started, and it was a fierce debate on the age of the sun, okay, that Aston did a remarkably interesting experiment, and what he was able to show is that the mass of a helium atom, is less than the mass of 4 hydrogen atoms. And if you were to take the atomic weight of hydrogen, you know that if you fuse, let's say, suppose I could fuse 4 of those hydrogens, then I can end up with helium. Okay, and it looked interesting that on the one hand, they found that the helium mass is actually less than the mass of 4 hydrogen atoms, and suddenly people said, "Oh, Mr. Einstein might be right," and maybe hydrogens are fusing together and forming helium and producing huge amounts of energy. Okay, and now there was another very important thing that happened. They were able to detect, in space, in the galaxies, in all over, large amounts of hydrogen and helium. So people knew that these things exist. These elements exist in our galaxies and everywhere. It was ubiquitous. Okay, and so but let me tell you, these were obviously these things happened at different points in time. Okay, and it was this great man, Arthur Eddington, Sir Arthur Eddington. He was probably the most famous astronomer at that time. That in 1928, Eddington for the first time suggested, that maybe the sun is powered by the nuclear fusion of hydrogen to form helium, and by Einstein's equation, E is equal to mc squared, it releases vast amounts of energy, and then based on the amount of hydrogen, helium, etc., that they had found, he actually said that now it looks like that the sun will probably last for 300 billion years, and so I hope you can see what a dramatic change happened over within a less than a century, and how important the work of Einstein was, that even Einstein would not have realized that, he would have been making such an important contribution that his work would be able to explain something so fundamental, that how the sun shines. Okay, but even then, it was still, it was only a hypothesis. What Arthur Eddington said, he just was clever enough to link up various things, and make this suggestion. Okay, but he did not prove. Okay, but what obviously strengthened the whole thing was that when they started estimating, the how old the sun has been, they were able to get a figure of around 4.6 billion years, and life on Earth, they were able to actually look at some of the fossil records, the oldest fossil records, and from that they concluded that life on Earth is at least 3.5 billion years old. Okay. Now, so what obviously Darwin said was absolutely fitting very well with this age of the of life on Earth, as was calculated. Okay, but that was not all. Finally, the hypothesis had to be converted into proof. Okay, and a very famous equation was proposed, by nuclear physicists. Okay, and what they said is, this is the equation: 4 hydrogen basically fused to form helium, but in addition, there are 2 positrons, positive electrons, which are produced, and also massless entities known as neutrinos, okay, which are produced, and these would be the carriers of energy, okay, and vast amounts of energy, okay, basically by E is equal to mc squared, and they really found that during this conversion, something like 0.7% of the total mass disappears, and is converted into energy. So that releases massive amounts of energy. Okay, and so later on, there were scientists who then started searching for these entities like neutrinos. Okay, and the person who discovered solar neutrinos basically actually was able to do an experiment and prove that neutrinos are actually bombarding the Earth from sun, and that person was Raymond Davis. And all these people subsequently were able to actually prove all these entities which arise from this equation, and each of those people actually won the Nobel Prize. So you can imagine that they were really great pieces of work which were done. And finally, it was only in the late 80s, okay, I'm just talking about not even 40 years back, okay, that the final proof was established that yes, indeed the sun is shining and releasing all this radiation because of nuclear fusion of hydrogen, okay, and that is what is powering life on Earth, and at least this will go on for 300 billion years, So I hope you can now see the connect between sun, solar energy, and what we know as the energy that powers the Earth. Okay, so when you say solar energy, remember that at its most fundamental level, solar energy is nuclear energy. Solar energy is not the visible radiation solar energy as we know it on Earth. Okay, that's only one manifestation. Okay, there are so many other manifestations of the solar energy. Just like Herschel said, by producing heat, okay, all winds are produced. So if you are hot about wind energy, remember it's linked to solar energy, and remember in turn that it is linked to nuclear fusion. Okay, tidal energy, all the water that evaporates and forms clouds and goes into rain and creates potential energy, which gives you hydropower. All of that is really powered by the sun, and in turn powered by nuclear fusion. All of the photosynthesis, everything, you know, it's just the manifestation of the nuclear energy on Earth is basically visible radiation and ultraviolet radiation. Okay, and that's what is used in photosynthesis. Obviously, you're not using nuclear energy at that kind of intense energy. So it's really amazing that everything finally is really all linked to nuclear fusion. And so what I want you to do is to take again a look back, and don't be too biased about any particular form of energy. Remember that they all have a common origin, and that common origin is basically nuclear fusion. Okay, now let us look at the global energy demand. Okay, and I've given it to you up till this was a projection which was made in 2007, is actually valid even now, and this projection goes on till 2030. Okay, so we are now here. Okay, 2021, right? So let us try and understand what is the composition of energy that is utilized in the world. I'm talking of these are global figures. Okay, so what you can see is coal. This is that red stuff. Okay, and you can see that coal, of course, has had remained quite flat for a while, but since about 2005, there has been a growth in the use of coal. Okay, there has been a massive growth in the use of oil. When I say oil, I mean fossil oil. Okay, which is derived from your fossil fuels, what you pump out of the ground. Okay, and so you can see what is found for oil. Then this is natural gas. Okay, that's gas over here. Right? Nuclear. We talk so much about nuclear energy, but it's a fairly small fraction. Okay, you can see over here it's just a few percent the world over. In India, it is barely 2%, not even 2%, 1.8%. Okay, so that's what nuclear is. Then you have got hydropower. Okay, you can see this is hydro energy, very, very tiny amounts. Okay, but then this is extremely heterogeneous. So there are some countries like Congo, which derives its entire energy from hydropower. Okay, because they've got the famous rivers, and so it generates massive amounts of energy. In India, our power generation actually started with hydropower, not with any of these other sources of energy. Okay, then you have got biomass. Okay, this is biomass. Okay, and then other renewables. Okay, it's here, right? So you can see the dominance of fossil-derived energy. It's just more than 75%. Okay, and you'll have to ask yourself the question that can this be actually replaced with renewable energy? Can it be done? when in fact the reality today is this. This is the reality. Okay. So this is the question. I mean, one is that we may want something, but whether that will ever happen is a big question mark. Okay, that you need to make a note of. Okay. Now let us look at global electricity demand. You know that most of our energy is, I wouldn't say most, a lot of energy is actually going into really producing, converting one form of energy into the other, and basically generating electricity. Okay, and let us look at electricity. What is the situation? Okay. Now, this is electricity, and again, you'll see by country. Okay, what is the scenario? So, and I'm not even going back to very old times. Okay, I'm just taking from 2000. Okay, and what you can see is the general view is that the requirement, as far as India is concerned, or as far as, let's say, United States is concerned, is quite flat. Not much of a change. Okay, look at the European countries, almost flat. Okay, Japan, flat. Okay, other advanced economies, flat. So their energy consumption is remaining virtually constant over 40-50 years. Now look at China and India and other developing countries. Okay, this is China. Look how it's grown. Okay, in 20 years. Just see where it was. Okay, it was barely 1/3 of the energy consumption, the electricity generation in the United States in 2000. And in 20 years, look at where they are today. Okay. Now, India has also seen a remarkable rise, okay, in power generation over 20 years. But if you have to, this is not 20 years, sorry, it's 40 years. So right now we are somewhere here. But even so, you can see where China is, and you can see where India is. India is not even 1/5, in terms of power generation as compared to China. Now, all developing countries are aspiring to grow, and that is the reason why the energy demand is skyrocketing. Okay, look how the situation has completely changed. Look what it was in 2000 and look what it is today. Okay, look at this. All right, so this is the importance of this course, that and in 2021 we are not even anywhere near what probably India will need to do if, let's say, all of our people are going to have adequate access to electricity. Today only a small fraction of our population has access to a lot of power, and typically in the cities, but not in rural areas. Okay, and so if you have to really increase their standard of living, then these things are going to grow. It has to, in fact, grow much like what happened in China. And so you can imagine the amount of power that will be required to be generated. Okay, and also what it means in terms of fuel that we will require to produce this power. Now, can somebody quickly work out for me, that you can see this unit, okay, it is actually, we are talking about in 2040, it will be 35,000 terawatt hour. Okay, 1 terawatt hour is equal to 1 billion units. because 1 unit is equal to 1 kilowatt hour. So 10 to the power 3 multiplied by 10 to the power 9, that is 10 to the power 12, which is your terawatt. Okay, and hour, of course, 60 seconds to a minute and 60 minutes to an hour. So if you multiply, that joules per second, 10 to the power 12 joules per second, multiply that by 3600, then that becomes equal to 1 terawatt hour of joules. Okay, and then this is 35,000 such terawatt hour. Okay, so you will know how much of joules of energy that basically means. Okay, I might ask you, in questions, some of these conversions, that how do you convert this into that? You should be able to do that. Okay. Any questions from anyone? Also, you can stop me anytime and ask me questions. Okay. Any questions?
Sir, could you repeat the conversions once?
Yeah. So, what is terawatt? Terawatt means 10 to the power 12 joules per second. Okay. Watt has the unit of joules per second, right? Okay. So, tera means 10 to the power 12, 10 to the power 12 joules per second, and terawatt hour means if I produce 10 to the power 12 joules per second over 1 hour, and 1 hour has 3600 seconds. Okay, so 1 terawatt hour means 10 to the power 12 into 3600 joules. That means so many joules per hour. You got it?
Yes, sir. Yes, sir.
Okay, and remember that when we talk about 1 unit of electrical power, we are actually talking about 1 kilowatt hour. Okay, that means 10 to the power 3 watts, being continuously released for 3600 seconds. That is how much energy there is in effectively 1 unit. So it will come out equal to 3.6 into 10 to the power 6 joules. Okay, 3.6 into 10 to the power 6 joules is equal to 1 kilowatt hour. Okay, and so that's how you do the conversions. It's all clear to everyone?
Yes, sir.
Okay,
Yes, sir.
and so like for example, if you're looking at biomass, you should be able to figure out like 1 kilogram of biomass. If I have to burn it, how many joules of energy do I get out of it? Okay, and so if I have to generate this many joules, how much biomass are we talking about? Okay, or if I say solar, and typically peak solar insolation is 1 kilowatt per meter squared. What is the area of solar insolation that I will require? And also consider that solar energy, 1 kilowatt hour is only the peak energy. Okay, and it lasts for only a few hours. Okay, so you'll be able to link up the actual energy requirement with the kind of energy resource, and how much energy is actually available from that resource. Okay, and we will do these calculations for wind, for solar, for biomass, okay, for nuclear. Okay, we will do these calculations as we go along. Is that clear?
Yes, sir.
Okay, now let us also look at another thing, and this is the nexus between energy and environment and sustainable development. Okay, like today, it's become very fashionable for everyone to talk about electric vehicles. Okay, EV. Okay, and it's amazing that people seem to forget where that electricity will come from, with which I have to charge the electric vehicles. Electric vehicles have a battery which will need to be charged, and then while it's running, it will be discharged and taken to be recharged. Okay, that is done with electricity. And where is that electricity coming from? Okay? Now, I'm giving you first what is viewed as the long-term scenario, okay, of electricity generation by fuel. You know, which kind of fuel will be used to generate that electricity, okay? Now, this is not what we have presently in India. I'll show you what we have, okay? But this is the global stated policy. Global stated policy says that roughly about 10% of the total electrical power will come from coal, you know, and another 7% will come from natural gas, okay. Another 2% or so will come from oil, you know. This much will come from nuclear, okay. This will come from wind. This will come from solar. Oh, this is hydro. This is wind. This is solar, the small one. And on top is renewable. Okay. And this is the situation today. And 2040, you know, they would like to basically, what are they effectively saying? That they will require more power compared to 2020, but that is not going to be through additional use of coal. Coal will remain where it is. Why? Because coal is a very polluting fuel. Okay, so they don't want to increase the amount of coal that will be used to generate this extra incremental power that we will require by the time we are 2040. Okay, so how are they going to achieve it? They want to achieve it by sourcing more natural gas, because natural gas is relatively cleaner as a fuel, but it's a fossil fuel. Any questions? Okay, you know, you can see that really the increases that they project partly will be from natural gas and partly from your hydropower, you know, and from wind power and solar, and some extent renewable, other renewables like biomass. You know, this is the projection. This is the stated policies. But if you go and ask people who are advocates of sustainable development, okay, all right, what they are saying is that nothing doing this will not give you sustainable development. Okay, for sustainable development by the year 2040, this must be the scenario. Okay, and you can see who is putting these. These are the international, you know, energy agency. They are the ones who are putting all this stuff. Okay, so it is not me, PK Ghosh, telling you this. I am only telling you what is the wisdom of people. Okay, and for sustainable development, by 2040, and 2040 is just 19 years from now. 2030 is just 9 years from now. Okay, and what they feel is that coal must go down by close to 50% in 9 years globally. Okay, and you can see that basically what they are saying also is that part of it will come also from reducing the total energy requirement. Okay, it is not going to be entirely about generate more. Okay, it is also going to be about conservation of energy. Okay, so there is partly conservation of energy and partly the energy mix, the fuel mix is projected to change. This is what all advanced countries are working towards. Okay, I hope you understand. Let me read out what exactly is meant by stated policies and sustainable development. In stated policy scenario, global electricity demand grows at 2.1% per year to 2040, twice the rate of primary energy demand. This raises electricity share in total final energy consumption from 19%. So today, out of the total energy, roughly about 20% is electricity, but that is going to increase to 24% by 2040. So it will be almost a quarter. Electricity demand growth is said to be particularly strong in developing countries, because developing countries are aspiring, to meet more of the aspirational needs of their population. So many of the people are below the poverty line. So many of the people don't have good access to electricity, etc. They are not as fortunate as we are. Okay. Government policies, market conditions, and available technologies collectively set a course for electricity supply to shift towards low carbon sources. Okay, and with their share increasing from 36% today to 52% in 2040. That is the stated policy. Okay, so there will be low carbon. So, for example, even natural gas is a low carbon source. You actually end up getting more energy when you burn natural gas, as for example, if you burn coal or burn oil. Okay, and that's why it is also considered to be a low carbon source. Okay? Now let's look at sustainable development scenario. In the sustainable development scenario, electricity plays an even larger role, reaching 31% of final energy consumption. Not 24%, 31%. In the sustainable development scenario, electricity is one of the few energy sources that sees growing consumption in 2040. And why is that? Because of electric vehicles. Okay, so if you hear a lot of talk about electric vehicles, etc., the reason is because of this. Okay, alongside the direct use of renewables and hydrogen. Okay, so it's not only going to be from those sources, like biomass, etc. The expectation is that there will be a large amount of hydrogen and renewables, which will come into play, and that's how they will achieve this 31% without in any way reducing the carbon footprint, and if anything, bringing down the carbon footprint. Okay, accelerated efforts on renewables, nuclear power, and carbon capture technologies rapidly decarbonize electricity supply, compensating for the sharp decline of coal-fired power generation and reducing power sector CO2 emissions by 3/4 by 2040. 3/4 of the value today, they want to reduce in 19 years' time. Now, you have to ask yourself, is this possible? Okay. And you will understand how difficult it is now if you look at the reality of India. Okay, so let us look at India, right? India in 2021, okay, this year, 2020-2021, produced 1382 terawatt hour of electricity. Okay, now what did we say this figure is? Okay, we said this figure, all right, is about 25,000 terawatt hour. Okay, that is all over the globe, total globe. And you can compare the 25,000 with 1382. And you will know what is our percentage of electricity that we produce as compared to the world. Okay, so please keep that in mind. Second, you need to know that the first power plant that came up in India was set up in Darjeeling, and it was based on hydropower, not based on coal or natural gas or any such thing. Okay, it was really the cleanest form of energy, hydropower. But as our requirement of electricity, power increased, the hydropower generation was simply inadequate. It could not really cater to any substantial requirement. And therefore, we had to look at those other forms of energy like coal and oil and natural gas, etc. Okay. Now, let us now look at what is the reality as far as India is concerned in terms of just coal. I'm not even taking anything else. Okay. Now, what did we say? What does the world want to do? The world wants to come from this, okay, to this, okay, from here to here. They want to reduce it by more than 50%, the coal consumption. And look at what is the situation in India today. This is India, okay. Now, this is only data for coal, mind you. If you take from 2004, around there has been a non-linear growth, okay, in power generation. It has been happening all the way from 2004, okay. Continuously, it has been going up. If anything, it has flattened thereafter. You can see how it was growing, okay, and then it is flattened, okay. And this data is from the Energy Research Institute in Delhi, TERI, okay. And so, and more importantly, also look at this. India did not even have all the requirement of coal, even though we are a country which is blessed with one of the largest coal resources, okay. Even then, quite a substantial amount of coal was being imported for power generation. Look at this. So even something as basic as coal, which is the only real fuel source that we have, is concerned, even there we are not self-sufficient. And the reasons for that I will explain as we go along. Okay. So, and now let us look at in India, what is the consumption of different types of fuel in generating this kind of a power, 1382 in 2021, 2021. Okay. So you can see that roughly about 53% comes from coal. Lignite is also a form of coal. So if you add the two up, we're talking about close to about 54-55%. Natural gas is fairly tiny, 6.5%. Okay, and hydropower is 12%. So although we started with hydropower, today there is maximum is about 12%. And it's going to get lower and lower because we do not have too many of extra hydropower installations coming up, and so as our power consumption goes more and more, what you will find is as a percentage, hydro will get smaller and smaller, because you have to build dams. Dams are you require appropriate rivers where you can build dams. So the situation is not so encouraging there. Nuclear power, we talk so much, just see nuclear, only 1.8%. Okay, and these are basically from renewable energy sources, but actually it is more of a wish rather than the reality. This is not even the reality because it's only installed capacity. Normally what happens is in renewable energy, only a fraction of the installed capacity is actually the energy that you actually generate, So even 25% in real terms may be closer to 10%. Okay? So what you can see is a heavy dependence on coal. Okay? In other words, we are completely out of sync with the rest of the world. We are completely out of sync with the global scenario. We are completely out of sync with sustainable development. We cannot have sustainable development with this kind of a scenario. It's not possible. Okay? Is it clear to everyone?
Yes, sir.
Okay. So I hope you can understand the gravity of the of the situation, and it's very important that any time, you want to propose something, yeah, ask yourself, always go back to these numbers, and ask what fraction are we talking about being able to fulfill with whatever I have in mind. You'll get I think you'll get a reality check, when you do that. Okay. Now, why is it that even though we have quite a bit of coal, why is it that we are still importing coal? The reason is we have a lot of coal, 301 billion tons of coal reserves. Although it sounds like a lot, even this is not such a huge figure, let me tell you. Okay. Now, the problem is that out of this, the good quality coal is just 5 billion tons. The good quality coal is the coal kind of, for example, which you require for producing coke, which goes into steel production. Okay, so that requires a very good quality coal, which is known as coking coal, and you can see we have just 5 billion tons of that, right? Then what we have is what is known as semi-coking coal. This is typically the kind of coal that is used in thermal power plants. But because thermal power plants are generating huge amounts of emission, and so people are searching for coal from other places, which are relatively cleaner. Okay, and relatively cleaner means maybe it has less sulfur, because otherwise it will generate massive amounts of acid fume. Okay, and here in India also there are about 9 states in all which generate, not even 9. I think the main ones are about 7. And these are the ones that generate maximum amount of coal, or they have the highest coal reserves. Odisha and Jharkhand and Chhattisgarh. These are the 3 big ones. Okay, but because of the poor quality of the coal, if you are going to use coal, we are going to have serious problem of emission, and we'll have to then look at technologies which will be able to clean up that emission. Or better still, if you can upgrade the coal, before it is used by carrying out some kind of a cleaning operation, and maybe then you'll be able to produce a coal which will be of better quality. Let me tell you that this is a huge opportunity. That is how to upgrade the quality of Indian coal. What can we do? Let us also look at what is coking coal and non-coking coal. All right, and the really biggest difference is the sulfur content. Now, if you are, as I said, I mean, like you will not be able to use most of our coal for steel production. And obviously the best quality of our coal will have to be kept for steel production. And we can only use the other form of the coal, right? Now, when you do that, as I told you, you've got very, very large amounts of sulfur, which one will have to deal with. Now, this is another thing that I want you to look at in this course. I can look at everything as a problem and a nuisance value, or I can look at it as a potential advantage. Okay, like for example, let me ask you, all of you are familiar with sulfuric acid?
Yes, sir.
Right. Sulfuric acid, as you know, is one of the largest commodity chemicals. Okay, huge requirement of sulfuric acid in for example, fertilizer production. Probably that's the largest requirement. And many other areas where we require sulfuric acid. A future technology could be actually then require getting the sulfur from coal. So coal could give you both sulfuric acid as well as give you the energy for your power plants. And that is the holistic way in which you need to look at each of these problems. The petrochemical industry has already done that. You see, when, for example, they are refining petrochemicals, okay, and they're removing all their desulfurization, all the good quality fuels, etc., that we have today, so from that process you generate H2S, and then from what is known as the Claus process, one ends up forming sulfur, okay, and that sulfur is then oxidized to SO2, sulfur dioxide, and then you have the contact process, and that's how you make sulfuric acid. Now the problem is that when fossil fuels, the oil type of fossil fuels run out, then where are you going to get your sulfur from? It's not going to be there. But I will be requiring sulfuric acid. So renewable energy resource does not mean that you will be so focused on renewable energy resource that you forget what are the peripheral activities and benefits that you might accrue from your feedstock. Okay, so keep this in mind. I will also point this out when we are talking about nuclear energy. Okay, later on.
The number of the power plants in India is reduced, and in that ratio, if the solar plants are increased, so we can achieve
so
that
very good,
target.
very good. But then you will have to look at what it means. We will do these calculations when we talk about solar. Okay.
Yes, yes.
And you can, but the question is, you can imagine the massive requirements.
Yes,
for
the
solar
generation
generation.
is much more less than the requirement.
Yeah, yes, your requirement, your generation. Today, if you take what is solar, you will have to grow maybe 100 times to be able
Yes,
to reach those kinds of figures. So it's going to be very, very tough for India to come anywhere close to these kinds of sustainable development goals. But
yes,
it is always good to have this in mind, to know the number and to know then that by what percentage am I deviating? Am I deviating by 100%, 500%, 1000%? What is my deviation? If you don't have those numbers with you, you can't do that. So that is the importance of numbers. All right. Now let us look at what is the reality, okay, in terms of oil, okay, and we look at all the things. It's not just oil, okay, but we will start focusing a bit more on oil because one of the real growth areas in our country has been the transportation sector. And as you know, the transportation sector is all dependent on petrol and diesel and things like that. So oil consumption in our country has grown by leaps and bounds. Look at the number of vehicles on the road. You'll get some idea of what the situation is like. All right. So first, I'll read out a few things just so that you know. Okay. The energy consumption in India is the fourth biggest after China, USA, and Russia. Okay, that's but then obviously that is not true about power yet. But it's getting there. The total primary energy consumption from crude oil, okay, natural gas, coal, nuclear energy, hydroelectricity, wind power, biomass electricity and solar power is 595 million ton equivalent of oil. Now, what happens is, as you know, all of these things will have different calorific values. So coal has a different calorific value, Natural gas has a different calorific value. Nuclear energy has a different calorific value. So what happens is that the best thing to do is to express these in terms of an oil equivalent, because we know what is the calorific value of oil, so you can correlate with that. Okay, that's what it is. Okay. Now, what you can see is that in the year 2013, India's net imports are nearly 144.3 million tons of crude oil, 16 million tons of LNG, natural gas, light natural gas, 95 million ton of coal. Okay, that is around 255 million ton equivalent. Okay, is actually being imported, which is about 43%. No, okay, and about 70% of India's electricity generation capacity is from fossil fuels, as we saw. India is largely dependent on fossil fuel imports to meet its energy demands. By 2030, India's dependence on energy imports is expected to exceed 53% from 42.9%, of the country's total energy consumption. In 2009-10, the country imported 159.26 million tons of crude oil, which amounts to 80% of its domestic crude oil consumption. And 31% of the country's total imports are oil imports. Okay, so if the oil prices go up, you know that we shiver. That's the reason. Okay, because it increases the trade deficit, the current account deficit tremendously. Okay, the growth of electricity generation in India has been hindered by domestic coal shortages. Okay, domestic coal shortages means good quality coal, the shortage of good quality coal. And as a consequence, India's coal imports for electricity generation increased by 18% in 2010. Okay. Now, you may have heard, for example, there's a lot of debate going on in Australia about Adani's having got some coal mines, and so they're going to dig out a lot of coal, but people are saying, look, I mean, this is not consistent with the sustainable development goals that the world is talking about, So there is a lot of controversy that is being created, because of these kinds of issues. Okay, so it's all linked with ultimate sustainable development goals. Okay. Now, this is again what you have to remember, that many times, we say things and we mean it well. Like, for example, we said that we want to reduce our oil imports by 10%. Okay, but in reality, so from 80% we wanted to bring it down to 70%. What is the reality? Reality is that it has increased to 84%. Not only has it not decreased or even stayed where it is, it has gone up to 84%. Now, can a country really sustain its growth agenda with this kind of dependence on import? It's not possible. Okay? And you will see how the situation is going to get worse and worse and worse. Okay, now let us look at, and so that you'll again understand, this is the global, production of oil between 1998 to 2020. I've dug out the latest. You can see July 2021. So this is the latest data. Okay, and what you will see is that it is something around 95,000 into 1,000 barrels per day is the unit. So 95 million barrels of oil is actually consumed in the world every day. What is one barrel? One barrel of oil is equal to 159 liters of oil. So you can multiply that by this figure, 90 million barrels, and that is basically, so something like maybe about around 15 million tons of oil is consumed in the world every day, every day. Okay, but still, you'll see in this figure that it is fairly flat. In fact, in 2020, it is more or less the figure of 2012. So this is the what is happening in the world. What is the situation in India? Look at this. From 2009, okay, our requirement has gone up by something like 50% or more, 60%, in a matter of what, 10 years, okay? And so we are again completely out of sync with what is the global oil consumption. Our consumption is continuously increasing, and that's why we are at 84% of imports. Why is it happening? Because everybody is going and buying an SUV. Okay, everybody, not one car. Today you've got 2, 3. I mean, even with the petrol prices at 106 rupees, 7 rupees, I mean, there is no shortage of anything, it seems. It's just going on and on. But you can see what is happening in terms of consumption. Okay, just have a look at this figure. Now, let me take you through the history of the world petroleum industry. And it is quite revealing. Okay, what is the first date? 1825, which is not even 200 years. Okay, now if you think that oil had existed forever, and it almost looks like it, now you talk to anyone, oh yeah, oil, we'll import it. When did it all start? It started in 1825. The first natural gas production plant was drilled, and it's not even 200 years. The first oil well was 1846 in Azerbaijan, and after that there has been no looking back. From 1846, okay, things have gone at breakneck speed. And why did that happen? Okay. It happened because a technology was developed to convert crude oil into kerosene. Then the four-stroke engine was patented by people in France. Rockefeller introduced the first oil refining company in the world. Okay. Edison invented the light bulb, and that had a booming effect on electricity. Then the combustion engine was invented in 1895. The Wright brothers flew the plane, and so you're talking about in our 117 years from the first flight by the Wright brothers, you can see what is the aviation sector, where today there is a massive jam, almost like a traffic jam of aeroplanes waiting to take off. It is just mind-boggling. Now, the first, you see, today we all say, oh, where is oil? It's from Saudi Arabia, Kuwait. When was it discovered? 1938. Just about 80 years ago. 80 years ago, oil was discovered, and these guys are now the dominant players. And what does it mean? That oil which was produced through the process of fossilization over millions of years, we have started consuming it and polishing it off in a 100-year time frame. It's just mind-boggling. Okay, how development has become completely warped with no relationship between our resources and how you conserve those resources, and how we are splurging and using them. There's no idea. It's just 80 years. Okay. Now, of course, there have been some supplemental sources like oil discovered in the North Sea, and then there have been huge upheavals in the price of oil, over a matter of something like 40 years, In 1 year, so the oil price rose from $13 to $34, then it collapsed, it again increased to $150 almost, at one point in time. Again, it collapsed. Last year, it collapsed very badly, and again, it is on the rise. Okay, so there is no certainty in terms of oil price. But let me tell you one certainty there is, that whatever may be the price, the oil reserves are coming down. Okay, and I'll show you to what extent it's coming down. Now let us look at, okay, what is the situation the world over as far as oil is concerned. Okay, this is India at number 24 position. Okay, these are our reserves. Okay, how many million barrels of oil, etc., that we have left, and what you will find is that we have only 0.5% of the global oil resources. Okay. Now, on the other hand, India and China roughly have around 40% of the world's population. India has about 20% of the world's population. Okay, with 0.5% oil resources. What else can you do but import? That's the reality. Okay, and so there's a, when you are looking at renewable resources course, remember that we have two problems. One is that we don't have anything, and the second is there is a massive pollution issue. Okay, so these are the two things which will simultaneously have to be looked at when you are looking at renewable resources, etc. And look at the quantum. What is the scale at which I need to do things? Then only you will know whether it's a viable strategy or an unviable strategy. Now, that's not all. Okay, it may be that let's say, not maybe, it is almost certain. Okay? It's almost certain if I assume that civilization will continue. If civilization collapses and we all die and that's the end of the world, matter ends there. I mean, then we are all gone. Okay, no need to worry about anything. Okay, but assuming that civilization is aspiring to be there for, after all, we have been there for thousands of years. You have records from the Harappan civilization. We go back to 5,000 years or longer. In so many other places you go, there are records up to 10,000 years, 20,000 years. And so when that is how long civilization has existed, and is there anything unreasonable in thinking that I want to at least live for another 10,000 years at least, that you want the world civilization to exist, before it all goes dead? And so the question is that what are we going to do? And I take it for granted that there will be some great innovation, and what will happen is that we will be able to meet our electricity requirements, through these great innovations. Okay, like one of you said that your vision is to see that maybe most of the plants will be solar power plants, which is great. Okay, may not be only solar, maybe wind, maybe nuclear, maybe whatever. But obviously we will have to, I'm pretty sure we will come up with something very, very remarkable in the area of alternative sources of energy, because if we don't, then our life is at stake. Civilization is at stake, is not going to survive, for sure. Now, but and for our energy requirement, energy related requirements of oil, you can see the breakdown. How much is high speed diesel, what is motor gasoline, okay, what is fuel oil, right? So these are all related to energy, okay, you burn them. But we do not use renewable or fossil fuel resources only for energy. We make fertilizers, we make pesticides, we wear clothes. All of those are carbon based. Okay, today. And where is that carbon coming from? Where are those materials coming from? They're all coming from effectively this oil or gas, which is being converted into different kinds of products, lubricants, okay, etc. Bitumen for road building. Okay? So, aviation fuel. Of course, these are all related to vehicles, but clearly there is a very large percentage of our oil that is required for other materials, other products like, as I said, drugs, fertilizers, etc. If there is no oil, as of today, or natural gas, there would be no urea, because the entire technology for making urea is basically dependent on natural gas. So you don't have natural gas, you won't have urea. But can we starve to death? No. So what we will have to do is also look at, even though the course talks about renewable energy resources, remember that our requirement is for renewable resources, not just energy resources. We need resources for other materials, and without that there would be no ICT, Institute of Chemical Technology is what? It's all technologies related to some form of carbon, whether it's dye stuff or specialty chemicals or name it. Okay. Where is it all coming from? It's all coming from fossil fuels. If that principal feedstock doesn't exist, there would be no ICT. Okay, so please keep that in mind also. Just to give you an idea of how important fossil fuels are, in the production of chemicals. Okay, and some of you said that you are interested in producing chemicals from renewable feedstock. Take one simple thing like ethylene, right, which you get from cracking of naphtha. Okay, and what does ethylene give you? Ethylene, I can make a huge consumption of polyethylene. Okay, it's probably one of the largest products, plastics. Okay, ethylene oxide, all your surfactants, etc., they come from ethylene oxide. Vinyl acetate, dichloroethane, from which I get polyvinyl chloride. It's such a huge, there would be no pipes. All your construction, all those PVC pipes, where is it coming from? It's coming from ethylene, which in turn is coming from your naphtha, which is coming from fossil fuel. Okay. There would be no, if I didn't have any ethylene glycol, there would be no polyester. Well, where would be your clothes? Which are majority is to the polyester. Your vehicles don't only require fuel to run. You need coolants. You need ethylene glycol. Okay, refrigerants. Okay, these are all used as refrigerants. So there is a massive, right, requirement of fossil fuels for materials. Okay, and that is also kind of directly competing with requirements for energy. So the wisest thing to do would be to conserve our fossil fuels, for carbon-based materials, because like nuclear power, nuclear energy, it can generate electricity. Okay, it can generate, that's fine. Okay, but I can generate carbon. with nuclear power, neither from hydropower, neither from wind energy, nor from solar energy. There's no carbon. But perhaps, yes, biomass, biomass can give me a combination of carbon and energy. Okay, so there are very, very serious issues, which we'll also need to look at. Alongside renewable energy, we also need to look at renewable materials, renewable feedstock for other kinds of products that the world requires. Now, let me ask you, how long do you think our oil resources will last? Just take a guess.
Sir, roughly 15 years more.
How many years?
15 years, sir.
15?
Yes, sir.
So what will we do after that?
Sorry, sir.
Close down everything.
No, sir. We are looking for the alternative, sir.
I know, but if you start looking now and it is going to end in 15 years.
No, sir, we already started, sir. Like electric vehicle is one of the biggest sector.
Vehicle, that's what I'm trying to tell you. Electric vehicle, all right? I mean, where the electricity will come from?
Solar energy, sir, I guess.
But I hope you can understand the scale of it.
Yes, sir. I am getting your point, sir.
Okay.
Yes.
So, but it is very important. Just like you saw, and you can ask this question, that if only 200 years back, the first natural gas production took place in the world, and civilization has existed for thousands of years, it is not as if civilization did not exist prior to natural gas and oil. So that gives us hope, that maybe oil finally you will see it in the when people write the history of mankind, maybe about 100 years from now, maybe it will appear as a tiny blip. Okay? What today it looks like a dominant thing will be a tiny, maybe 500 years later, people will say, really? You had something like oil? Is that so? That's what is going to happen. And so let us look at some of the projections of how long world's oil reserves will last. Okay? Now, this estimate was made by British Petroleum. British Petroleum, as you know, is one of the largest oil companies in the world. Okay, and what I don't want to go into the details of it, but effectively they have said, okay, and this is, by the way, in 2030. Okay, they made this projection. So 8 years is already over. So from 53.3 years, you deduct 8 years, you're left with about 45 years. Okay, so their estimate is that oil resources will last only another 45 years. Okay, now, I mean, and let me tell you that increasingly this is being viewed as probably correct, Okay, so just imagine 1825, okay, was the first production of natural gas. Oil, let's come to oil. Baku, 1846. Okay, so we are at 2021. Add another 40 years, so 66 years. 2066. 2066 is nothing. All of you will be what? You'll be around 80, 85 years old or so. Okay, around that time. Okay, 85. By that time, people will probably live till 120 years. We will all be gone. We will be somewhere else, but you all will be alive, and you can actually make a note of it today and look 85 years later or 45 years later in 2066, and say, hey, what did we predict then? And what has happened? Okay? It will be very interesting. Now imagine a resource which had existed, which took millions of years for nature to produce. We, out of our greed, have gobbled it all up in 250 years. That's it. Okay, just imagine. So that is certainly the antithesis of sustainable development. Okay, it is a completely non-sustainable development. Okay, now this figure is also not as if British Petroleum just said it in 2013 through some magical waving a wand. You know. Around 1956, you can see this person Hubbard. You know, he was working in Shell company. Okay, and in 1956, you know, Hubbard made a prediction of how long our oil resources will last. Okay, and he came up with this curve, which is known as the Hubbard curve. I might ask you some equation on trying to calculate some numbers and things based on this equation. I'm not going to go through the equation in detail, you know, but what is very interesting to see is that in 2020, this is where we are already at the declining phase. That is, things had peaked around 2000. This was the maximum proven reserve. This is basically how it is now declining. Okay. So by the year, and this is, so in 30 years time, 2050, you know, we will be at about 30% of today's reserves. You see, this is a growth trend. So by this growth trend, you know, you can imagine if I extrapolate this to 2050, what will happen? But the reality is very different. The reality is the Hubbard curve. Okay? And so you can imagine, I expect that in about 10 years' time, massive wars will start, you know, and people will be fighting, you know, they will be, why are people so worried about Afghanistan and Iraq and this, that? Because people want the control of the oil resources. Why is America so mad about shale oil? That's because they're trying to stretch from 50 years to 70 years, you know, how long it will last. But what is 50 years and 70 years in the eons of time? You know, I mean, surely we all want to live. Your grandchildren will want to live. Your grandchildren, your children, your grandchildren will live in the 22nd century. There's no oil then. What will they do? Okay, and by the way, the US Energy Information has a similar production of how long things will last, and you know, this is the latest data, you know, and these are the proven oil reserves, and exactly as Hubbard had predicted. You know, it's just amazing. What a great man he was. That beyond 2013, you know, the proven reserves have become flat. There is no increase in the proven reserves. Okay? So we know exactly how much is available. Okay? And every year we consume about 2.1% of that proven reserve. And that's how you know you come to a figure of around 40 to 50 years is how long your oil will last. It's all based on data. Okay, that is the reality that we have to reckon with. Okay, I hope you can see what you have, and look at this. Okay, the population is 7.3. We are at already 20% of the population. Okay, the population is projected to rise in 2050 to 9.7 billion. Obviously, we will require more energy, and look at what will happen to the reserves. There will be only 20% remaining. Can you imagine what a battle is going to be? And please look at all those terawatt hour and million ton oil equivalent, etc. All these numbers, anytime you propose something. Now, what will also happen is very interesting. Uh, the IT sector, information and communications technology, it looks so magical, no? Everything, you just press a button and things are happening. Okay. And probably by 2050, what you'll have, I suspect, is that you'll see a reduction in the number of human beings, and you'll see a massive growth in things like robots. Okay. It's already there. I mean, there are already robots which have been introduced, and this is only the cradle time. It's just starting. Okay, so in about 40-50 years, I expect, because in any case, for example, all vehicles, you're not going to have drivers. They're all going to be driven by automatically. Your most of your factory production, etc., will happen by robots. And so human beings are not going to be required, okay, in that many numbers. Okay? And of course, when human beings are not required, then one expects that their population will probably fall. It will not go to 9.7 billion. It may drop, to something like 6 billion. Who knows? What will happen? Because otherwise, we will in any case kill each other to death. When we are fighting for resources. That's what will happen. But there is a lot of focus being given on the IT sector. But please, for a moment, do not think that the IT sector is not energy intensive. The IT sector consumes huge amounts of energy. Okay. So, for example, the global total energy production, electricity, we found was 20,000 terawatt hour of electricity. You can go back to your previous slide, around 2020. And if you see the figure here, 2020, we are talking about something like 3,000 terawatt hour is linked to ICT, linked to information and communications technology. That's not a small sum. It's about 15%. Okay. And look at the exponential growth that is being projected. So what will happen is that the ICT sector is actually going to end up consuming huge amounts of power. And it's so fashionable for people to say, oh, I store everything in the cloud. But each time I'm uploading and downloading things, you just don't know how much energy is getting consumed. Okay. And so electricity requirement is not going to come down, it's going to go up massively. And if robots are going to again take over, robots are going to require huge amounts of energy. So the energy situation is really not going to improve that substantially, even with the introduction of ICT. So we will have to ask ourselves, what exactly is going to save us. But as you saw, the percentage of requirement of electricity in the total energy portfolio is going to get more and more. And so if we have a breakthrough in one of the energy sources, like you may say solar, I may say something else, but doesn't matter. Then it may be possible that we will be able to generate that additional amount of power. Today it doesn't look likely, but the situation could change 20, 30 years from now, and that's what this course is about, and we will discuss those technologies. Okay. Now, what I want you to do is that I want you to do a couple of assignments. Okay. And you could put it down and you could send it to me, and then I might ask one of you to present in the next class or in one of the future classes. What I want you to list out is prepare a comprehensive list of why is absolute energy demand increasing. Okay. Now, one, of course, we know that doesn't take a genius to say. So the first one I'll write down for you. What is the first one? What should we write? Why is
Increasing population.
wonderful. Growing population. Okay. So this is your first bullet point. Okay. And what I want you to do is that I want you to add to the list and think of everything. Okay. Why absolute energy demand is increasing. Okay. And we will compare with some data, from other, generated by some of the other previous students and things like that. We'll see how it compares. Second, I want you to also prepare a list, of how to reduce energy consumption. Okay, I mean, the only thing you will not say is that kill everybody. That's the best way to reduce the energy consumption. But other than that, how to reduce energy consumption. So, for example, let's say, suppose I were to take one, and what are we seeing in reality today? We are seeing massive use of personal cars. Okay, whereas, if we had much greater use of public transport, we can reduce energy, right? Right or wrong?
Yes, sir, definitely.
Yes.
Right, sir.
Okay, so let us do one. Let us put substitute private vehicles with public transport. Okay, let's just take this as the first point. Now, I want you to add many more points to this. Okay? All right.
Yes,
so
sir.
this will be your second assignment, right? How can one reduce energy consumption?